So, okay, well, it turns out there's actually some things a lot better than that. Phase change heat transfer is an outstanding way to remove heat. I'll talk about three different mechanisms, but all three of them are a significant improvement over, even forced convection. So boiling is one of the best ways to remove heat, remove heat from something. So if I have, and it basically comes from two facts. So the water would be the typical boiling fluid, although there's a bunch of other ones too. But if you think about water has a heat of vaporization on the order of 2 kilojoules per gram, meaning that basically I don't have to necessarily even remove the chunk of liquid from the area. I really just have to convert it into gas, and I've already sort of stored energy in that gas. But it comes with an extra benefit, which is that gas is significantly lighter than liquid by about 1,000-fold. And so there's a very strong buoyant force that pulls bubbles away from a surface. So in effect, you get, it's sort of like a forced convection where the force that removes the bubbles or the vapors of vapor is essentially provided intrinsically by the process. And so these can have very large heat transfer coefficients. I'll give numerical values on the next slide, but typically these are 100,000 times better than natural convection, and I'm really not making that number up. Condensation is just as good and usually better, actually. So condensation happens whenever you have a surface that is surrounded by a saturated vapor, and where the surface is colder than the saturation temperature. So if that happens, liquid will start condensing on the outside of a surface, and you can transfer a lot of heat that way, very, very effectively. A third option, which is somewhere in between, is evaporation. Evaporation, I find, is often confused with boiling, but these are actually not the same process at all. Evaporation is helped by a lot of similar principles. Essentially, the heat of vaporization is essentially converting all that heat very quickly, and then the vapor is very easy to get rid of because it has a low viscosity. So you can remove a lot of heat this way, but the mechanism is actually different. Basically, evaporation occurs because if you have whatever the surrounding vapor is not at a saturation pressure, meaning that it's not at equilibrium with the liquid, the actual liquid that's on the surface you're trying to transfer heat from. And so you can have a conversion of liquid to vapor, even though it's not really a boiling process. Basically, if the vapor pressure at the ambient temperature turns out to be less than what could be handled at that temperature, then you'll get transfer by that process. So again, I'm just going to build up this list a little bit higher. I'm not going into the details of how you figure out these heat transfer coefficients, but just to give you some idea of how big they are, if you go to some tables for pool boiling, you pull up heat transfer coefficients on the order of 1,000 to 35,000 watts per meter squared Kelvin, where the 35,000 is not particularly hard to get, actually. Film condensation, so actually in the last slide I didn't really differentiate between different types of condensation, but there are actually two different types of condensation. One, what I'll call film condensation, where the liquid condenses entirely on the outside of the object that you're trying to transfer heat from, or transfer heat to. So in that process turns out to be very effective at transferring heat with heat transfer coefficients on the order of 20,000 to 70,000 watts per meter squared Kelvin. But it turns out that it's even better if you can so that's not the only choice for how you can get condensed things. So let me remove my picture from here. If it's possible to have a surface where rather than condensing a continuous film, if you can condense as droplets, It turns out that that is actually a lot better for the heat transfer because that allows any newly condensing stuff to essentially go around the liquid, which is essentially acting as a resistive barrier and a thermally resistive barrier, and allows it direct access to the solid to condense new stuff. And so essentially the thermal resistance of that process can be a lot less. And a lot of times this can be promoted by using gravity to remove the droplets. So if you have, let's say, a hydrophobic surface and you can essentially avoid generating a continuous film at some point, then a lot of times those droplets will remove themselves by gravity. There are also schemes that you can mechanically try and remove the droplets, but then you have to be careful about not using too much energy for that process.